Amazon, so that should be useful for y'all. And then we'll talk about, so we've secured our cloud, but security only lives next to usability, and it's only secure as usable constructs we provide our staff. And we're going to finish with looking to the future, where we think the solutions are for companies that have concerns as great as Bitcoin companies do today, and things that we think the rest of you can start applying as well. So to jump right into it, so before I worked in cryptocurrency, I did have a more conventional job. So I spent the last 5 years before this at NASA's Jet Propulsion Laboratory, where we started experimenting with cloud, where we had traditional data centers, but we wanted a burstable capacity next to the deep space network to process larger capacities of data as soon as it had come home from space. And we took that a little further to process more sensitive data. And so for the data that we wanted to process, we weren't comfortable at the agency with processing on just any public cloud and putting our data somewhere else. What we really needed to do was to pull that cloud inside of our environment, and we would only process it if we control the walls around it. And so for those of you that use Amazon's SDK, you'll often see a 10th region that you don't have the ability to enumerate, and that's Amazon's Gov Cloud that we helped pioneer with Amazon to process slightly more secure workloads. And we've segued that into now designing some of the more secure clouds for Coinbase. So at Coinbase, we're the largest consumer-facing Bitcoin wallet today. And can I get one more show of hands? Does anybody own any Bitcoin today? Awesome. And could you keep your hands up if you rolled your own crypto to create your keys, or you've got some key splitting scheme that you designed for that? At least one person, and he works at Coinbase. But yeah, so we really like this touring this space. This is something that's attracted some really hardcore cryptographers to work with us at Coinbase. And when we're thinking about designing something securely, we like to draw inspiration from Fort Knox, which is where some of America's gold reserves are stored. And they're stored, in fact, in the center of a military base. And with the walls and protections and security measures they put around it, it's so secure, no one's ever actually even tried to break inside. And so a lot of what we're doing is putting enough controls that we really feel like the core and center of our company is something our customers and the rest of our staff can trust. And that's an especially unique challenge for us in our space today, where we're looking at revolutionizing or transforming a fairly traditional industry. This is a video of how money used to move, okay? So security around money used to be physical. Armed guards, walls around our banks and our vaults, and when this would move, it had actual protections around it, sharded, of course, by the amount of value that you could fit in any one of those items. This, however, is money moving on our exchange. And so we publicly show how much is traded every day. So we've traded on the order of hundreds of millions of US dollars since we launched this in February. And when money moves in cryptocurrency, it moves immediately, moves irreversibly, and when it's gone, it's really gone. So we don't have some of the physical luxuries that we used to have to split our reserves out across more traditional security measures. And so for us, we need to make sure every single transaction, every single place our keys have touched is treated with the utmost security. And we think of this as one of the driving pillars for our company. So we use the word security on our homepage like many of you, but we really think that goes to the core of who we are and what we do. So we like to think that we exist and survive with security. We survive by moving fast. We're still a startup. The cryptocurrency space isn't nearly finished innovating yet. And we're fueled by having the best team. And to talk about how this team is learning from some of the people that have come before us, we think of our role in the industry largely as maturing to make this accessible for larger and larger audiences. And I'm sure many of you have seen some of the big Bitcoin companies in the news since maybe 2009 or 2010 when it really started to achieve prominence. And I'm going to pass it off to my colleague Olaf here, who's going to talk a little bit about how we're learning from Bitcoin's past.
So thanks, Rob. So I'm going to talk a little bit about some of the historical, security problems that other Bitcoin companies have faced. I'm not going to name names, but I'm going to talk in some detail about the types of attacks these companies have seen and how they have fallen to certain hackers. So this is an email I sent to my friend about 1 week after I found out about Bitcoin back in June 2011. So I said the primary risk is not with cryptocurrency as a protocol, but with the security of the websites on which the trading takes place. So I was interested in this exact problem shortly after I found out about Bitcoin, and I've been pursuing it ever since. So My background is I wrote my undergraduate thesis on Bitcoin, the protocol, and the path to mass adoption and what that would look like for society. So I've been thinking about this for a very, very long time, and I think there are some unique things to Bitcoin that make it a particular security challenge, but one that we're working very hard on solving. So the first thing to know here is that Bitcoin, I consider this the perfect storm for hackers. And the reason I say this is Bitcoin has some certain characteristics that make it very easy to extract value once you're in a network, right? So a lot of times a hacker might gain access to a network, but it might not be obvious how they can extract that value. So sometimes it is obvious, it might be credit card numbers, sometimes it might be a database of user data, it might be a bit more complicated. With Bitcoin, it's very, very easy because it's pseudonymous, international, irreversible, and instant. Basically, the moment they have access to those private keys, that Bitcoin is gone, and that Bitcoin is overseas. And these hackers, I will go over 3 case studies here, none of them have been captured. And I think that's very important to note, that this is the type of crime where you can maybe steal $100 million and not get caught. And people won't even know which continent you're on. So there's a few basic security principles that we have used as the underpinning of our current architecture. And these are based on some of the mistakes that other companies in the space have made in the past. So I'm going to go over each of these principles and a case study to support exactly why we have that. So the first one is that third parties are compromised. And so I'm going to go over what I'm calling the attack in the cloud. So this is a company that was hosting their servers on, a virtual network. And basically, the intruder was able to access from a web-based customer service portal. So I think there's a couple takeaways here. One is you cannot have the security of your Bitcoin based on a single password from one customer support rep at a third-party vendor. So your vendors are never going to take security as seriously as you're going to take security. So you might have this bomb shelter attitude, but a vendor here might be a really simple backdoor, and one password might be enough to get into your keys, right? So I think this is a pretty amazing thing as well, that once the hacker was able to get in, they're looking at a number of different websites hosted on these servers, and they just searched the word Bitcoin, right? And they only targeted the 8 customers who had mentioned Bitcoin. This led to 46,000 Bitcoin being stolen. So I think a really good lesson here is once hackers are in, they're going to try to extract value however they can. So this is a picture of safety deposit boxes. And once they're in that vault, they're just going to go for the company that has the most value for them. So they could have just as well searched credit cards or emails or anything. And we've seen, like, for example, with the Ashley Madison hacks, a kind of alternative way of extracting value that might be bribery or, I'll release these emails unless you pay me, things like that. So they're always going to try to extract value once they're in the system, however they can. So the second principle here is that everyone in your org is a target. Okay, so what I mean by that is looking at this photo here, who has access to your sensitive data? And this is something we think about a lot, both in terms of employees, third-party vendors, people physically at the office, things like that. So in this particular compromise, the database was recording cold storage addresses, and it was recording the balance of those addresses. Every time the hot wallet was getting low, so these are the Bitcoin stored on the server so that we can actually operate the exchange, this particular company, when that hot wallet was getting low, they were auto-pulling from cold storage. Well, the reason I put cold in quotes here is that that's not really what cold storage is. So, the question might be how cold? I think that's actually not the right question. Cold storage is either air-gapped and it's cold, or it's not air-gapped and it's not cold. So in this case, it's, I think, not accurate to call this even cold storage. It's really just an alternative way of storing Bitcoin on the server. If every single time that your hot wallet's getting low, you're just pulling from that cold storage and refilling that hot wallet straight away. So a couple lessons here, one is that the blockchain, this is this irrefutable distributed ledger. Let's actually use it, right? Let's not just depend on this database field that's telling us how much Bitcoin is in our cold storage addresses. There should be an actual flag here looking directly at these cold storage addresses on the blockchain. So in terms of the attack itself, an employee altered the database for 6+ months, just telling, saying in the database, oh yeah, these cold storage addresses have plenty of Bitcoin in them. When in reality, on the actual blockchain, the actual addresses were being drained slowly for 6 months. So a good question here is, was this malicious intent or coercion? And I think it doesn't really matter. That's not the interesting question to me. The most important thing is to just realize that every single employee and every single person who has access is a target, right? And that might be because there might be this insider threat that they're going to go rogue, but also if you have access to these keys, now you are a target, right? So there might be bribery, blackmail, any number of things involved. So I think an important takeaway is multi-signature, right? So M-event access to these kinds of sensitive pieces of data so that there's no single point of failure and no single individual who has access to this kind of data. So in the third attack, I think the number one takeaway here is that attackers are very sophisticated. So the last two might have just been a customer service password was compromised. The other one was maybe a single point of failure where too many employees had access to cold storage. So in this one, we're just going to talk about very, very advanced phishing attacks. So these attacks were tailored to the individual interests of the employees who were working at this company. So a lot of research had been done on exactly what the interests of these employees were. So looking deeply into the background of these people, noticing things they'd done 5 years ago that would pique their interest if it was reintroduced in an email. I think a big takeaway here is that you will see spear phishes via Skype, Facebook, LinkedIn, any sort of social media. It's important to recognize that these things aren't going to always happen via your work email at 2 p.m. while you're at work, right? When you're checking your Facebook messages on mobile on Sunday morning, that might be where the attack is happening. And these might be extremely sophisticated, targeting particularly your interests and things that you've done in the past to kind of blend in and make the spearfish much more believable. So looking at the timeline of this attack, I think this is pretty amazing. The phishing messages started coming in April, but malware was not successfully downloaded until November. Okay, so we're talking about 7 months here of consistent phishing messages targeted via social media, tailored to specific interests for 7 months until the malware was successfully installed. But when we're looking at the actual bounty on the other side of this, a lot of people in the world will work for 6 months in order to get maybe $5 million, right? So just in the way that we're sitting here at our desks trying to secure our companies, there are people in other parts of the world sitting at their computer just trying to hack your company. And I think it's important to understand that these attackers might be extremely patient and wait, this is a 7-month-long persistent attack. And I think another takeaway here is when you're thinking about how to defend against this, you can't always run your red team at 2 p.m., right? You need to be ready. They are going to attack at that perfect moment. So a kind of summary of that timeline, the persistence there was 8 months, and they owned the computer for 53 days before actually draining the hot wallet. I think that one is really fascinating. So once they had malware installed in this computer and they had access, they waited for a very long time to wait until the perfect moment to actually attack. And this maximized the extraction, right? They might have done it that night, but instead they waited for a very, very long time, nearly 2 months, with total backdoor access to this administrator who did have access to the keys of the hot wallet. And 18,000 Bitcoin were stolen. So they were able to extract a lot of value by being extremely persistent, extremely targeted, and patient, basically waiting 8 or 9 months to complete this entire attack. So those 3 case studies kind of inform a lot of the principles that we have designed our architecture around. So you can never trust a third party. They're never going to take security as seriously as you will. Everyone in your org is a target, whether by malicious intent or whether they will be coerced or in some other way compromised. And then these attackers are sophisticated, and you have to always assume that they are. So with that and those principles based on these historical compromises of other Bitcoin companies, I'm going to pass it back off to Rob, who's going to explain a little bit about securing our cloud infrastructure.
Excellent. Thank you, Witoff. So people might be spending 7 months or more focused on you, focused on your administrator, focused on getting inside. That's a tall order to defend against, but I think this is indeed a solvable problem with some of the new ways we're applying those principles inside. So I'm going to run into some of the details on how we're actually implementing those today. And now the first question that I think we've sort of begged here is, so we said securing our cloud. So if we really care about security, why use a cloud at all, right? Why not lock these servers up in a closet in our back room or put these away in some more secure location? Well, we thought about looking at several new architecture designs when we were looking at designing our latest infrastructure that we recently migrated to inside Coinbase. But there were three things that we kept coming back to. The first was maturity. We, of course, wanted to run on some provider that we could rely on and provide a dependable service to us. We wanted to have some other service that people were already familiar with, right? Recruiting is still an important project for all of us to continue growing our companies and stay competitive. But the last thing that really worked well for us to move into a public cloud was the idea of incentives, where when we look at the largest public cloud provider, the aggregate capacity that they're providing is 5x the next 14 providers. They're doing multiple billions of dollars worth of revenue every quarter. And so with the amount of support that they have in their cloud, even one small security incident, regardless of which customer that's for, would cause such irreparable harm, we think, to that provider, that the incentives are really in our favor to partner with some of the large public cloud providers today. And so that's ultimately why we decided to build our new infrastructure inside of AWS. And so we are using their public cloud regions today. And we do appreciate how securely they take security. In fact, that this isn't actually a picture of Amazon's infrastructure. This is a picture of one of their competitors. I cannot find any pictures of Amazon's data centers. So when we're then choosing the partners that we do want to work with, it's important that for those partners, we have to be very selective, but we also can't rely on any single one partner. This is a screenshot from a blog post that a very sharp pen tester put out, realizing that the two-factor solution that a lot of us were using at the time was actually susceptible to a fairly simple bypass, right? So for a large period of time, the internet's a large part of their two-factor tokens were pretty easily bypassable here. So even those protections that we think we put in place are not always something we can rely on. So it's important to have multiple tiers of vendors and multiple levels of protections. Two-factor alone is not a silver bullet. What we then augment that with is we rely and work very heavily on public bug bounty programs. So a lot of other companies have preceded us. I think Facebook did a tremendous job really defining what a good white hat program looked like. This is a current snapshot of our bug bounty program. And something we believe really strongly with is that we do not partner with vendors if they don't have a clear white hat program. We know just like our infrastructure is not perfect, our vendors and partners' infrastructure is also not perfect. And we want to make sure that when there's a vulnerability in that, it's disclosed in a responsible way and not exploited against our vendors and ultimately used against us. Okay, so with that, we did decide to build our latest infrastructure inside of this cloud. And so for that cloud, I split up four major pieces that we focused heavily on to define security within. And the first of those was the root tokens that ultimately protected our clouds. And some of you may have seen there was a startup a couple years ago, there have actually been a few since, that had accidentally checked their root tokens into GitHub or some other public repository, which led to a really bad time. And there have been whole companies that have actually shut down because of that. So when we talk about the core of our storage, we also like to get our root tokens as cold as possible, and not just slightly cold, but actually in an air-gapped, truly cold type of fashion. And that's the same thing we do with our cold storage. Just like Olaf mentioned, the Bitcoin keys that are behind Coinbase for our cold storage are completely kept offline. They have only been created and used in an air-gapped manner, which works really well with asymmetric crypto. We then, and we have a blog post that details quite a bit of this, we originally had somewhere around the order of 97% of our funds were fully stored offline, but we've been able to increase that, so just about 99% of the Bitcoin that we own are fully isolated in a truly cold and air-gapped environment. So that's where a large chunk of our security begins, and that's really important for us to mitigate the possible extent that any single breach can reach. And so we also believe that this is how your root tokens for your cloud should be treated as well. So for those of you using AWS, you can create a soft token or also get a hard token. We only use hard tokens for the core root tokens on our account. And when we get those tokens, it's really important that they be stored fully offline. We actually put these in vaults and safes to make sure that in the event of some kind of emergency, those root tokens are still within our control, so multiple Coinbase parties can come together to release those root tokens to gain super admin access to our cloud. These are not things that are easy to get access to. We intentionally have friction in front of this, but this is something that protects us in the event of a disaster to truly be able to get back our clouds. Once we've locked away the root tokens for our clouds, we then have this challenge of needing to provide permissions for the rest of our staff to properly use this and use some of the best practices that we're all familiar with. Now, I think one of the driving visions that's really pushing infrastructure and thereby security today came from DockerCon this year, where Salman Hikes talked about this vision of, in the next 5 years, building a software layer to make the entire internet programmable. This is not just empowering an engineer to spin up a server, this is empowering an engineer to sit behind his or her terminal and create whatever you might want at whatever scale you might want. Truly being able to control the internet at the tip of your fingertips. And I think this is a tremendously powerful driver for a lot of engineers to move quickly. New startups can spin up really fast. One engineer can do a tremendous amount of things. And so one question we find ourselves constantly asking ourselves is, why would an engineer choose to work at our enterprise over a superpowered terminal? If security at our company is going to mean we're going to slice and lock up privileges and slow down our engineers, I, as an engineer, might just want to work somewhere else where I can move faster and have more fun. So one of our principles that's constantly driving us is this idea that engineers really do choose, and we need to empower them to move really quickly and to move effectively without the potential for major security breaches or disasters on the other side of that. Now, for those permissions we have, there's some obvious things we want to do, like least privilege, no escalation, standard things. I'm sure there have been other talks at AppSec so far about that. And that last piece, self-service, is really important, where that's where we believe we don't want to have a security team between our engineers in production. We want to have a security team that's empowered our engineers to move more quickly within the confines of what is really safe. That company I mentioned before led to this article. We're reflecting on cloud. Something that's really nice with cloud is that there's an API call to do anything, including deleting your VPC, terminating all your servers, and closing your account. Actually, there might not be a call to close your account yet, but there probably will be soon. And so this is something we really have to design out. So one of those principles that we push on is this idea that no one at Coinbase should be able to accidentally the company. And we think when we've restricted the ability for engineers to have those mistakes or to accidentally leak creds that allow escalation inside of our cloud, we provide this environment that engineers can move around freely in. By providing a safe environment for our teams to try new things and flip things upside down, we think we can actually move faster, and that makes it a more effective environment and also a more secure environment. Now, for those of you in AWS in particular here, for the markup language provided to us to control access to our clouds, it turns out policies are actually fairly hard. So this is using Amazon's identity and access management. Last we checked, there were 1,191 actions and over 40 services to know how to apply these the actions within IAM across. And that's compounded by the complexity of resources and ARNs and condition restrictions as well. And there are even some fairly benign things that we might want to do inside of IAM, like EC2 describe star. For anyone using almost any third party in the cloud that's looking at your usage, your cost, the type of instances that you're using, you have given this permission in probably a blanket fashion to that vendor, all of their employees, and when they're breached, the attackers that have breached them as well. So when we look a little bit deeper at what you can actually do with that describe star that I would venture to guess almost everyone in the room has shared with your vendors, we can look at underneath that API call are a few things grouped, like instance type, is it optimized? But that piece at the bottom is something that has often gotten missed, so user data, right? When we launch a lot of our servers in the cloud, the recommended way is to adjust the user data on what you're launching. You might put your environment variables or your tokens in there as well. And it turns out that if your vendors have access to describe star, which is in every read-only permission set that I've seen, they can also describe all of your envars, all of your secret key material, and all of the things that you're actually trying to hide. So this is a pretty bad thing. We actually had one of our partners in the past year who was susceptible to this type of vulnerability, and the disclosure for it came through our White Hat program. So this ended up costing us several $1,000s, but in the end, I think are hopefully helping people to learn a valuable lesson on that as well. okay? So when we then look at how we actually want to protect our IAM actions, where there are there's a subset of IAM actions that we really can trust. It's typically managed where all of your engineers might be a user inside of IAM. Your user can create keys that you would embed in your applications, and those keys would be assigned certain policies. And the policies define what kind of permission sets those keys can have access to. It turns out there's one other function or one other way of assigning that as well, where we don't have to just use policies, we can also use groups. And so this leads to how we manage our permissions and our policies inside Coinbase with this idea of self-service IAM. And this is something we open sourced almost a year ago now. And the way that we use this is by using the IAM variable capability inside of our policies. And so what we allow our users to do is every engineer inside Coinbase can create more users. We don't want to restrict them and force them to go off to some security team who maybe isn't in, maybe they can get around to it next week. No, we allow all of our engineers to create their own users inside of IAM. However, we restrict that so they can only create users within their user namespace. So I, Rob, can create Rob-Project1, Rob-Project2, but I can't touch or create Olaf-Project1 or Julian-Project7, right? We're starting to namespace IAM here. Once we've started to namespace that, we then give ourselves the ability to add and remove those, we call them service users, from predefined groups. So we're also relying on the namespace here, so I can add my Rob-Project1 to some other predefined group that we have. And we restrict those groups, so they're only, you can only use a predefined set of groups that our IAM wizards have reviewed and verified. We don't have an accidental describe star where it can really be harmful to us. And so we can take this a little bit further even into S3, which has a really nice implementation of this, to further namespace within S3. So the Rob-Project1 user inside of IAM can only manage Rob-Project1 buckets inside of S3, and we provide predefined groups that provide read, write, metadata, and manage access to the variety of services that we have inside. And so this has helped effectively make IAM usable again for us without providing put policy or some way of escalating privileges across our entire fleet, which is something we really have to avoid. One of the superpowers that Ulf and I talk about a lot is attackers have gotten very good at moving laterally inside of infrastructures, and if you have keys that can escalate, they sure will be used to escalate and cause some potentially irreparable harm. So those are things that we've tried to design out, not by providing some finesse solution that looks at what's been created and audited once every 30 minutes, design out so engineers can't even create something that could potentially subject them to harm. That's how we think we're making a safe environment for engineers to really move quickly. What this ends up looking like inside of our AWS panel is something like this, where we have a lot of IAM users inside. There will be one main engineering user with lots of sub and service users underneath that. The groups that we then provided look something like this, where we restrict to that service namespace inside. So under service, there's then a AWS service like S3 or EC2 or auto scaling, elastic load balancing, whatever else you're using inside. And then we have different levels of access inside. So this is something that we've open sourced on GitHub. There's a variety of CloudFormation templates that'll help create these automatically for you. As there are an increasing number of services, increasing number of API accounts, there's probably going to be a whole new set of services released at reInvent in a couple weeks. We would appreciate your help if you'd like to join us in making these more granular, providing more groups, helping us really get to least privilege with this kind of self-service IAM approach. That's something we'd really like to work with the community on as well. Now, while we're on the topic of GitHub too, so keys in GitHub has been a hot topic recently, right? People accidentally committing keys, and some malicious party uses them to spin up all sorts of Bitcoin miners on EC2, spins up a $10,000 bill, and then you have to negotiate with AWS how to bring that down. That's something we also don't ever want to have happen. We realize that it's perfectly feasible that at some point our keys will probably make their way accidentally into some public forum. As much as we'd like to protect against that, that's something that has become a reality for our industry, right? This is happening, and this is something we want to embrace inside Coinbase. So what we do is on all of our keys, we're really tight on the conditions that we've applied on them, okay? So there are 3 main condition restrictions we apply pretty liberally. The first is enforcing secure transport, of course. We don't want anyone accidentally using our keys over the public internet over HTTP. That would not be good for any of us or any of you. The next piece, which we use selectively, is there are some API calls that we don't actually want the ability for unauthenticated or non-two-factored users to build applications around or automate. Things like creating new users inside is something that we actually want to protect. And so that second protection, forcing multi-factor on API calls, effectively protects us from using IAM keys and enforces that we use the AWS console for that. And now this last piece is something that has been really important for us, the source IP restriction. This doesn't work on every single AWS service today, but it's something we're working with Amazon on. But this is something that protects us from when those keys are accidentally pushed to GitHub. So it turns out that for those of you using a NAT layer or another isolated set of public-facing IPs inside of your account, you can, from Amazon, get a CIDR block delivered to you. And so we have our own Coinbase CIDR blocks inside that our keys will not work outside of our environment. So if our EC2 keys were accidentally shared, they're not going to work in the public GitHub unless you're already on the Coinbase production or corporate or other network inside. Okay? Now that we've started to secure and made our cloud a little bit usable through those keys, we've then got to design a network that those keys can be used within. And so we take the whole methodology for this, right? At some point, we will all be breached. There will be some security hole across our environments. And so we design with a lot of little environments so that when there's a hole poked in our ship, it doesn't take down the whole cruise, right? Now, inside of AWS, they provide a few constructs that make this fairly usable. The first is the idea of consolidated billing, right? So for the account we're using to pull metrics, to pay our bills, to pull in other accounts, we will never run a single server within that account. That's one isolated account, and underneath that is where the rest of our accounts fall. So our corporate account, of course, falls below that. You probably all have something just like that as well. We have a development account on one side of that. And on the other side, we have a variety of production accounts. And we've split this across our corporate, so when we're in development, when somebody accidentally uses a production key in development, that's fine, it's not going to work because there's no actual routable path between development and prod. And a subset of these tie back to our office environment. This is something we've had the chance to truly design, I think, cloud first, where our corporate environment is in the cloud, and that bridges back down to our office network. And our actual topology is mirrored directly from that. So that dev corp prod is something designed just like we have here. There's no routable path from dev to prod. And on the other side of that, there are some cases where we want to get a little bit more secure, where our hot wallet is stored or where our private keys actually live. So those have a further isolated environment. We also want to embrace where engineers want to experiment with new services for whatever is released at reInvent. Our team is probably not going to wait for us to update our self-service template so they can use it. So we do encourage our staff as well to have a personal, private, experimental account. They'll link this under our consolidated billing account so they can experiment with new services without having any routable path or shared resources with our internal Coinbase environments. Okay. Now, when we have an environment like this, the way that artifacts are typically deployed to production, and there have been a few services discussed at AppSec that we actually pretty strongly disagree with their design. The way this typically works is that in your local environment, we might be developing or testing locally. An engineer might then push some of their artifacts to a development or test environment. Once they run properly there, we might run to a staging or CI or CD environment inside our corporate network, which might then push out to production for the really secure stuff when we're modifying how we're signing transactions or integrating with the next upgrade to the Bitcoin protocol. We might then push that out to our audit clouds or our really top secret environments. And for those of you that notice what's wrong with this, when one of our engineers has someone spearfish them after a 7-month campaign, from your development environment, you can now traverse, from your local environment, you can now traverse out to dev, where you can then go to corp, and you can then go to prod, and then you can get all the way out to our edge nodes. And that's something we can't allow. So what we do is we flip this model around, so we never have direct environment to our development cloud or the next cloud or the next cloud. What we can instead do is only propose changes. So from our local environment, we can propose and say, hey, development, this is some new code that I'd really like to run. And then living within development, we have certain validations and checks that'll say, okay, that's great. Are you an employee? Okay. Are you supposed to have access to this project? Okay. Have we launched this project before? Has it been reviewed by security? Okay. If so, then we can run it in development. We have a series of increasingly strict checks as we get further and further out to production. So if and when there's a popped laptop on our network, that's fine. There are validations that will block deployments, or when the next Xcode ghost happens, this starts to protect us from deeper layers in our infrastructure, okay? And once we've gotten this whole environment working, we need to provide this so our engineers can actually use it. And so as much as we love the network design, all the checks, all the validations we have in here, one of the hardest projects for us is to make all of this work invisible, right? This is something our engineers do not want to have to understand the details of. And so we instead condense this down into really only two environments inside. We have a development environment and we have a production environment, and that's all the engineers have to know. And so we've distilled a lot of this up to the development tools we provide our staff, okay? So I want to zoom in a little bit on that environment to show you what that practically looks like at the next layer, okay? So in our development environment, we've got a lot of things running right now. And for what's running inside, the very base of that is the images at the bottom, so our AMIs that we're running. For those AMIs, Amazon provides a couple nice ways where we can pull those AMIs from. There's the Amazon Marketplace, right? At Coinbase, we are 100% Docker in production, so we've really embraced the latest in Docker. We really like not having a package manager or other unnecessary pieces inside of our environment. So we are running CoreOS inside. And so when we're pulling CoreOS, we'll start with a snapshot that CoreOS has provided us, validated to make sure it's exactly what we've got. And when we pull that from the marketplace, we want to make sure what we get is CoreOS, not something that's CoreOS-ish, right? So there's a lot of poorly configured images that anyone can publish there, right? And we want to make sure those don't make it into our environment. So at the bottom of our stack, we're running the same hardened, secured CoreOS box everywhere. And all of the variability inside of our environment comes with Docker containers inside. So I'm then going to talk a little bit about how we're making that sort of security usable. And so we have this really nice split between our base image and the Docker containers on top of it. And this has worked really well because Docker is actually a really elegant interface for engineers to quickly adopt and feel like they have full control over their environment. But we now have our own layer between engineering and infrastructure and security, where infrastructure and security can fully harden and monitor and wrap around our containers, which is really powerful for us without having to overly deeply integrate with those teams. It's a really nice layer of abstraction for us. So we have that one configurable pillar that's been hardened, and we have many containers, which we're then wrapping around and further hardening by the base AMI. Now, across those many containers, we do a couple things to that box to make sure it's hardened and running in a way that is good for our security teams. And one of those is we modify the OEM cloud config. So we always make sure that when a box is started up, all of our logging tools, our monitoring tools, our stats tools are always running. And this is a great interface and abstraction with Docker because these are running not by instrumenting our engineers' code, but it's running fully around that environment. We also use server spec, where just like we test the rest of our code and we put security checks in there, we want to have these security checks in our AMIs and operating systems as well. So whenever we push a new OS out, we'll always launch at least some reasonably large number, typically around 50 of them, to make sure we've checked all of them for race conditions, edge cases, and the other versions of software deployed on them. Now, for talking about security with Docker, this has been a hot topic, and I think Diego was here talking about some of their security pieces as well. We think a pretty good analogy for how we're viewing security with Docker today is actually Elasticsearch, which we love. This is one of my favorite databases today. In 2010, Shay Banian had a blog post that said, I'm launching Elasticsearch here, this is what it's going to do, wrapping Lucene, this should be fun. 4 years later, after that first blog post, they had another blog post from Shay, which was for Shield, for security. And so it took them about 4 years to really get their security story straight, and they're still tuning it, but it took them a while to really understand it. And so we think we're taking a similar approach with Docker, where we do not rely on any of the security features Docker has provided today. Instead, we only run mutually trusted containers on the same hypervisor. Right? So we might run a web server next to a cache that's needed for that web server, but between all of our different artifacts like web and API and our admin tier inside, we use hypervisor layer security. That's what we know, that's what we trust. We might look at Docker security in a couple years, but we're not going to rely on this in the near-term future. This is further good for us, and especially so with Docker, because every time we deploy inside, we don't have a multi-tenant problem where we have to optimize all of our box usage. Whenever we deploy, we physically burn all of our hosts down to the ground. This is a great thing in cloud. Spin up fresh hosts that have been re-hardened. There's no legacy, there's no cruft, there's no atrophy on that server. These are always fresh, and so we can always, at the touch of a button, destroy our whole entire environment and bring it all up fresh. It's been really good for us in security. So That idea of mutually trusted containers has been fantastic for us. We believe when one container is compromised today, all your containers will probably be compromised if you're doing something smart with multi-tenancy without having a full SE Linux or kernel optimization team inside your company. Okay. That then scorched earth approach we take, where we're constantly burning all of our hosts down, is really important. When we were testing before we fully migrated onto our new AWS-based infrastructure, we launched over 10,000 servers in the process of getting that up and running, which made sure that the place that we're in today, at the touch of a button, we can roll everything, right? Really good for us, really bad for attackers and APTs, knowing that we're pulling all of our logs off all the time, okay? Just like we had the issue we mentioned with the AWS Marketplace, where any old image can be pushed up there, the same is really true with Docker, where it's amazing that you can run Redis in one line at your terminal, but you can also run maybe the Redis you didn't want to run, or a version that isn't quite secure. So we do a couple things and make sure we run our registries inside, so that when we're pulling, we're never pulling Docker pull Redis or Docker run Redis. It's always in the internal Coinbase registry, which the security and infra teams have looked at. They've hardened, made sure these are things that we want to be running in our environment. I'm going to skip over this piece because we've got running out of time. One of the pieces OWASP talked about was patience, right? Attackers might be spending 7 months or more just to get inside our infrastructure, and years too, to get at the value that we're all storing inside. Well, something we have that we've built inside that's we think is helping us combat this is the idea that we're always watching, right? We've got that architecture where we have the base AMI and all of our containers around, so we get to instrument and log absolutely everything. And by using some of the modern streaming tools we have inside, we're doing that in real time. So in real time, we're watching every single thing that happens around Coinbase. We process and monitor over 1 billion events per day, so that when we're sitting around looking at what's happening, looking for indicators or other types of metrics inside, we feel like we have full visibility into everything that's going on without having to SSH into all of our hosts or run some script to pull everything down. It's always in real time being monitored in one place where we can look at an overall view of our infrastructure. And so the 3 things that we want to be able to do with that monitoring and logging stack is to know what's happening. After we know what's happening, we want to be able to make decisions based on that information, and we want to have that actionable intel now. We don't want to wait. We don't want to wait for someone to traverse deeper into our infrastructure. And so in our environment, we're running all these containers and all these hosts we have inside, but a subset of those hosts are those containers I mentioned that are just there for monitoring. And those monitoring containers are running in a couple types of ways. We're pulling all the systemd journal output off of all of our boxes in real time. We're doing the same for LogSpout, which is pluggable for those of you that like writing Go, so we're pulling all of that off of our host in real time. We don't actually store those logs in our host at all, so our environment is really designed to encourage you to use our streaming infrastructure, and our boxes are decreasingly usable, which is something we like. The fewer things we have in our boxes, the lower our attack footprint is. Now, all those containers are sending their data. We use Amazon's Kinesis for this. You can use Kafka, Storm, if you're a Twitter, Heron, whatever the next thing is that comes out. And we can pull all the information out of our production environment. So after we've tokenized and sanitized some of that, we can process all of that with a fleet of containers that can be easily updated and looking for other items inside in real time. We also like to use Kibana for this quite a bit. We have a nice Kinesis to Elasticsearch adapter underneath, which has been really powerful for us. Now, this has this nice effect where as we get more and more products and services, where we used to just have a website, now we've got an exchange, now we've got multiple mobile apps. For all of those data producers, there are a lot of transformations we want to provide on them to maybe add geo to an IP or de-anonymize some of our information or even tokenize some of that so we don't share it too widely. And then ultimately consume that through other tools that we have in our infrastructure. But this architecture is traditionally not scaled very well where we get this exponential growth. And we think typically you end up adding new producers and saying, I don't want to add it to that infrastructure, too many things to plug that to. So we start to decrease the value of our log stack over time. But what's happened that's really nice is by using a streaming core at the base of this, we have this nice linearization effect inside, where we've effectively removed the exponential growth and complexity from producers to consumers to ways of interacting with that data, and had this real nice linearization effect where all of our consumers have access to all of our data and all of our logs in real time. They might not care about a large portion of it, but they have the option of using it to give them as much operational insight as we can possibly provide. And now one example that may hit home for some of you where this has been really nice for us is picking on a couple types of logs we pull in from development, our production web, some of our vendors as well. We're pulling all this through. Just like all of you, we've got our list of IOCs inside, right? And in that IOC list, we know on some of our tools that might be subject to attack, or we might have information that someone's planning to attack a part of our infrastructure. And so we'll look for those IOCs, intending to see them in our web stack. Now, in that web stack, we saw this alarm go off not too long ago where we saw an IOC, but it wasn't where we had actually designed or intended to see it. This was coming from a totally separate vendor. And so though we had intended to see our IOC from web logs, we actually saw it come through our vendor logs, right? And so this was an unintentional boost in security awareness because we were using this real-time streaming infrastructure inside. Now, we had removed and tokenized some of the sensitive data for that, but we had other tools at our disposal to look at what that actually was. And so this has helped bring the mean time to response for our IOCs down to a much larger set of data producers to a much smaller time frame. Okay? And now, the last piece that I want to jump to conclude on is this idea of consensus deployments. Okay. So we're going to wrap up on these slides. On this idea of consensus deployment, we really like the idea of designing out single point failures, of which we include humans as a single point failure. And so I mentioned we've distilled a lot of our infrastructure to really simple, usable tools where engineers can press a few buttons to deploy. One area where we've already been embracing this idea of consensus-based actions is actually through Git, where anyone can propose a change to a pull request to a repo, but not everyone can approve it, okay? And we've embraced that so that inside, anyone can propose a change to our environment, but just because you propose a change does not mean that you can deploy it. Our deploy buttons are not activated by default. We can then, once a pull request has been opened, we have a little robot inside that'll say, hey, this is great that you proposed a change, but before we can merge that to master, we're going to need someone else that didn't work on this to review your code and approve it. Once we then get at least one or sometimes two or sometimes even three other people that plus one and review that code for security audits, we then have our robot say, okay, multiple human beings have unlocked this. No single point failure, no compromised laptop or spearphished admin credentials have tried to deploy this. And that then unlocks this for a merge to master and ultimately deploying further inside our infra. And so that's embraced this idea of, just like with a nuclear weapon, no single person can fire that. We always require in Coinbase multiple people to turn the key to push that deploy out. And only once that's happened can we enable our deploy buttons to actually start pushing things out through the further validations across our different tiers of our network. And so to wrap up, where we really see the future of security and where we're designing a lot inside Coinbase today is this idea of three-phase consensus. We really like to empower engineers so that anyone should be able to propose a change to production or any artifact inside, but it's that layer where we're achieving consensus, where we don't like any single human point of failure. Once we've achieved quorum to approve that, anyone should then be able to apply or hit that deploy button and initiate the next process. So finally, what we've tried to run through here, and I hope this was useful, was one, embracing the past, really learning from who's come before you. Securing our environment by design, not putting handcuffs on engineers, but giving them a way where they're empowered to design and deploy their own artifacts. Looking at and monitoring everything in real time and converging through a stream processing core where possible, and providing the ability to escalate permissions with consensus. That's that last quorum or consensus process that I showed. So that's what we're up to at Coinbase. Thank you so much for having us at AppSec, and I think we've got maybe a couple minutes for questions. One question up front.
Yeah, your slides are very awesome. May I see like the first slides, because we missed the recording and I wanted, so if you can just redo the first slide, like the first three of your deck, that would be great.
Yeah, so maybe we'll,
after the questions.
yeah, we'll review some of our slides. If you want to come up afterwards, we can do that. Thanks.
That was my question. Great presentation. Are the slides available?
Yeah, we can make these available. We'll put them on SlideShare within a week.
The recording as well.
Even better.
I'm curious, do you let employees work from home
Yeah, great question. So do we let our employees work from home, and when we're achieving consensus, how do we know it's actually our employees? The short answer is that we don't know that any single quorum approver is indeed an employee. And that's why we require multiple human beings. We do some cryptographic signing inside, which starts to verify identity, but in the case of full compromise, that may not even be trusted. So that's why we fall back on multiple humans being able to approve that.
Would they link in, like, it's possible to identify everybody that works somewhere and target?
It is, yeah. So we are hedging on the fact that our environment and our staff aren't completely compromised inside. So our thesis is that for someone to fully traverse all of our staff laptops, we put a tremendous amount of logging and monitoring in place. So for someone to fully own our environment, we think we'll catch that. We don't have a solution against every admin or every engineer being compromised today, though.
I may have missed this part, but there was a conversation around AMIs. And is there a process that you usually use for vetting AMIs that are pulled in from the marketplace?
Yeah, so is there a process we use for vetting AMIs that are pulled in from the marketplace? So we do look at cryptographic signatures of some of the binaries that are installed in our OS. We're using Core OS today, which is also really nice for that because it has a really small footprint. So the amount that we have to scan is very small. After we have pulled an AMI that's been published to us from Core OS, we then have a series of Packer and server spec tests that will run through that and verify everything else on that. We have another process for vetting the Docker images that come inside, but those are two things that are also important for us.
Are code reviews ever been included in cases where there's an AMI using, let's say, like, that's specifically containing an open source tool of any sort?
Yeah, so we do look at public, so for looking at other public libraries that are pulled in, we do rely on publicly available audits of some of the specific versions. We tag all those versions. We have for every build of our code, we'll look at the security state of all the packages that we pulled in there as well. And maybe one more question.
Okay, now it works. So how do you secure the communication inside your applications? Like when applications talk to each other or talk to other AWS services? Do you do roles, IP restrictions? Do you enable TLS in every communication? How do you deal with it?
Really good question. So how do we verify security and encryption and identities we're talking within our network? There's a lot of service discovery tools that we like a lot, but very few of them have full authentication and namespacing and real smart roles inside. So we really like to use traditional things here. We use a lot of DNS inside, which is a little more static, but it's a little more trusted for us. We do have TLS everywhere inside. We do also verify with custom certificates across our environment. And so maybe we'll conclude there. We'll have some time to hang out up front if anybody wants to join us, and thanks again for having us.